In this video, we'll explore infinite series. In particular, we'll talk about infinite geometric series. It's very important to understand geometric series before we talk about infinite series of other types. This video should come with a disclaimer because it does discuss infinity, which is a notoriously difficult thing to understand. Consider, for example, Zeno's paradox of Achilles and the tortoise. In this paradox, Achilles, the fleet-footed hero of the Trojan War, is engaged in a race with a lowly tortoise, which has been granted a head start. Achilles' task initially seems easy, but he has a problem. Before he can overtake the tortoise, he must first catch up with it. While Achilles is covering the gap between himself and the tortoise that existed at the start of the race, however, the tortoise creates a new gap. The new gap is smaller than the first, but it is still a finite distance that Achilles must cover to catch up with the animal. Achilles then races across the new gap. To Achilles' frustration, while he was scampering across the second gap, the tortoise was establishing a third. The upshot is that Achilles can never overtake the tortoise. No matter how quickly Achilles closes each gap, the slow but steady tortoise will always open new, smaller ones and remain just ahead of the Greek hero. Of course, we know that this argument is flawed. And even Zeno, the author of the paradox, knew it was flawed. He just wanted his contemporaries to explain the flaw in his thinking. And the difficulty lies in the fact that we think that when you add an infinite number of things, you must automatically get something infinite. And we'll see in this video that that is not always the case. Let's start with some definitions. A sequence T of n is said to converge if there exists some real number L, such the value of T of n becomes arbitrarily close to L as n approaches infinity. This number L is a real finite number, even though we're considering an infinite number of terms in the sequence. The number L is called the limit of the sequence, and any sequence that does not converge is said to diverge. Let's explain convergence of a sequence using an example. Find the limit of the sequences below as n approaches infinity. Our first sequence is 0.99 raised to the nth power, and our second is 1.01 raised to the nth power. The question is, for both a and b, is there a number, an L, a limit, in which a or b get arbitrarily close to as n gets larger? Pause the video and think if you can come up with an answer. We can show that the limit as n goes to infinity of a sub n is equal to 0. Meanwhile, b sub n does not converge. That is to say, it diverges to infinity as n gets large. Here's how you can tell. As I write out the terms of a sub n, the sequence, I notice right away that the terms are getting smaller, from 0.99 to about 0.98 to about 0.97. If I imagine what happens as I zoom forward to the 100th term in the sequence, 0.99 raised to the 100th power is about 0.366, substantially smaller than where I started. If I zoom forward even further to the 1000th term in the sequence, 0.99 raised to the 1000 power is 0.00004317 or thereabout. What we're seeing is that by going far enough into the sequence as n approaches infinity, traveling far enough into the sequence, I can make the term of the sequence, the value of the term, as close to 0 as I would like. I went out to the 1000th term, and I can see that I'm almost at 0. Of course, there's no term in a sub n that actually ever reaches 0. However, I can get as close as I would like. If you wanted to find a term that was smaller than 0.00000001, you could do that in the sequence a sub n. You just have to go far enough out in the sequence to find it. Meanwhile, with a sequence like b sub n, that's not the case. When you look at the first several terms of b sub n, you know that notice that the sequence is growing. 1.01, then about 1.02, then 1.03. If we zoom out to the 100th term of b sub n, we find that 1.01 raised to the 100th power is about 2.7. A little bit more than 2.7, but about 2.7. If we zoom out further still and find 1.01 to the 1000th power, we find that 1.01 raised to the 1000th power is 20,959 and change. And so what we can see is that there is no number L that b sub n is going to approach. Instead, it's going to keep growing without bound. And that's what does not converge means when we talk about a sequence. Note that both of these sequences were geometric in nature. For A, the common ratio was 0.99, and for B, the common ratio was 1.01. And I chose those examples on purpose because I chose a common ratio that was a little bit less than 1 and another common ratio that was a little bit greater than 1. And this is the dividing line that you want to think about when you think about geometric sequences. Whenever the common ratio is less than 1, we would see the sequence tend to 0. Whenever the common ratio is greater than 1, we would see the sequence grow without bound. And what's more, I can actually add absolute value bars around my common ratio. Because if I used either of these examples with, say, a minus sign, the same conclusion would hold true. So as long as the magnitude of the common ratio is less than 1, which is to say that the common ratio is between -1 and 1, we would have a convergent sequence that would tend towards 0. And whenever the common ratio was bigger than 1 or smaller than -1, well, then we're going to have a geometric sequence that does not converge, that diverges. Understanding geometric sequences is the first step to understanding a geometric series. And geometric series are what we're really concerned about. We're asked here, what does the geometric series converge to in the infinite case? So recall that we already have a formula that can sum a finite number of terms of a geometric series. It's a plus ar plus ar squared plus the nth term ar to the n minus 1. And that formula, just to remind you, is a times 1 minus r to the n over 1 minus r. If you want to add up the first 10 terms, the first 100 terms of a geometric series, then this formula will do the job. What we want to know, though, is there a limit to that sum, right? We want to consider the infinite case. So the infinite case instead looks like this: a plus ar squared plus ... We just go on forever. We never actually stop at the first 100 terms. Well, it turns out that this infinite sum formula is actually very easy to calculate based on the one we already have. You see, in the nth case, we're dealing with an r to the n, this r to the n term right here. And we already considered on the previous slide what happens to a common ratio like 0.99 to the n, or 1.01 to the n, as n grows large. And since any time our common ratio was less than 1, we knew that r to the n would tend to 0. Well, that means that term just cancels out in the formula. It goes away. This term will disappear entirely. It'll be a big, giant goose egg. And so our infinite sum will just be an a in the numerator there, multiplied by the quantity 1 minus 0, which is just 1, over 1 minus r. And this is a formula that we can use for any infinite sum. But be careful, the only time you want to use that formula is the case when r is less than 0. So 2 quick examples. Example 1, if I have 1 plus a half plus a quarter and so on. And then the second example, if I have 1 plus 2 plus 4. Okay? In example 1, the formula says my infinite sum will be 1, because that's my first term, over 1 minus a half, because my common ratio is a half. And 1 over 1 minus a half is 2. That infinite sum is indeed 2. Meanwhile, in example 2, the formula, if blindly applied, would give me 1, first term still 1, divided by 1 minus 2, since the common ratio is 2, times 2 to get to the next term, which is, of course, negative 1. And that second one is nonsense. It's nonsense to say 1 plus 2 plus 4 plus 8, and so on, added infinite number of terms and get negative 1. That's not true because we didn't follow this very important rule, which says you can use this formula only when the common ratio is less than 1. What do you do otherwise? Well, what you would say is this sum diverges. And that's clear that if I just keep adding larger and larger numbers, then my sum is going to be an infinitely large number. In this example, we're asked to find a sum, an infinite sum, given in sigma notation. I recommend that you take the sum and write it out in expanded form. Plugging in k equals 0 gives you 1. Plugging in k equals 1 gives you minus 8/9. K equals 2 plus 64 81st. K equals 3 gives you negative 512 over 729. And this series continues on like this, alternating between positive and negative. I can see that this series is indeed geometric, and A, the first term, is equal to 1. See that right there. And the common ratio is equal to negative 8/9, because that's what you're multiplying between each term. Well, I'm going to put a big check mark next to negative 8/9 because that is indeed in the interval in which a geometric series will converge. Negative 8/9 is between negative 1 and positive 1. And thus, I can work out this series using the formula we just developed, A over 1 minus R. 1 over 1 minus negative 8/9, which is also known as 1 over 1 plus 8/9, which is 17/9. And of course, 1 divided by 17/9 is the same as 1 times 9/17. And so my sum will be equal to 9/17. It's entirely possible that in the last example, you could look at the sum in sigma notation and know that the first term in that series was 1 and that the common ratio in that series was equal to negative 8/9, and then jump right to A over 1 minus R and work out the answer. However, every problem will not necessarily be that easy. In this problem, I have a more complex looking expression in sigma notation. And so what I would like you to do is pause the video and write out the first 3 terms in this sum by plugging in n equals 1, n equals 2, and n equals 3, and then tell me what A equals, the first term in the series, and tell me what R equals, the common ratio, assuming, of course, that it does appear to be a geometric sum. When I plug in n equals 1, I find that the first term is 25 out of 32. When I plug in n equals 2, I find that the second term, which is added on, is 625 out of 1024. When I plug in n equals 3, I find that the third term is 15,625 out of 32,768. This implies that the first term in this series is 25/32, and when I look at the multiplier from one term to the next, I find that the common ratio is also 25/32, which means the infinite sum that I'm asked to find here is 25/32 divided by 1 minus 25/32, which of course is 25 out of 32, over 7 out of 32, which of course is 25 out of 32 multiplied by 32 out of 7, or 25/7. If you wish to look at one of these problems and try to algebraically manipulate the expression here so that it falls into the general formula AR to the K minus 1, so that you can quickly check that the common ratio is indeed less than 1, and then quickly use the formula A over 1 minus R, that's fine. It's also fine, however, to write out a few terms and investigate it that way, term by term. You see that A is equal to 25/32, and you can quickly calculate what the common ratio is and then plug into the formula. Let's look at one more example. Which of the following series converge? At first glance, it might appear that they both do, but take a closer look. Pause the video and determine whether A, negative 2/3 to the K, or B, 1/4 to the negative K, will be a convergent series. If you said that series A converges, while series B diverges to infinity, you would be correct. Here's why. In series A, when I write out the terms, I get negative 2/3 plus 4/9 minus 8/27 plus 16/81, and so on, and thus the infinite sum is negative 2/3, the first term, divided by 1 minus negative 2/3, the common ratio, which is the same thing as negative 2/5. Meanwhile, when I look at series B, I might first be tempted to say that the common ratio is 1/4. However, upon closer inspection, I see that this is raised to a negative exponent. So when I plug in terms, I get that series B is 1 plus 4 plus 16 plus 64, and so on, and this clearly diverges to infinity because the common ratio R is equal to 4, which is definitely greater than 1. In this example, we see an alternating sum. When you plug in 1, you get negative 1. When you plug in 2, the negative 1 squared to make a positive. For 3, it's negative again. And it goes on like this, on and on and on, infinitely. And in this example, we see the danger of the common ratio not being strictly greater than negative 1 or less than positive 1. These inequalities that we require to use the formula A over 1 minus R are strict. That means if R is equal to 1 or negative 1, we have divergence. And here we see why. If I sum an even number of terms, like these, for example, then I'll get that my sum is 0. Meanwhile, if I sum an odd number of terms, like this, I'll get that the sum is negative 1. The fact that the answer conflicts for even and odd terms leads us to say that this series does not converge. Does not converge. It wouldn't be fair to say that it diverges to infinity because it doesn't. It either adds to 0 or it adds to negative 1, depending on if you stop after an even number of terms or odd. The one thing we can agree upon is it doesn't converge on any particular number. In this example, we'll show how you can write a repeating decimal as a fraction. For letter A, which we'll do together, we're looking at the repeating decimal 0.121212, and so on. We can write this as an infinite series. The first term in the series will be 0.12, or 12/100ths. The next term needs to account for the second 1, 2, which of course is over a few spaces. So I'll leave some space, 0, 0, and then add the 1, 2. So right now, when I add these two decimal numbers together, I get 0.1212. If I'd like to keep going, then I'll add more space, 4 zeros this time, right? And I'll keep following this particular pattern, this time 6 zeros, and so on. This, of course, is an infinite geometric series. I can identify very easily my first term right here. This is A sub 1. So I put that in the numerator. And I can also clearly identify the common ratio. Since I'm moving the decimal point over twice, that means my ratio will be 1/100th, or 0.01. And so 1 minus 0.01, this ends up giving me 0.12 out of 0.99, or 12/99ths, or if you prefer to reduce the fraction, 4/33. Pause the video and give letter B a try, which is the decimal 1.234234234, and so on. The important thing to note with example B is that the repeated pattern doesn't include the 1. It's only 2, 3, and 4 that repeat. So when I write out the sum as a geometric series, I should see this. This term will have 6 zeros and then a 2, 3, 4, and so on. And so I can find this geometric sum using the formula. It won't include the 1 because the 1 doesn't fit the pattern. However, I can add the 1 on separately and still get to my answer. So my final answer will be 1 plus my first term, which is not 1, but instead the first term of the geometric pattern, divided by 1 minus 0.001, or 1/1000th. When you do the arithmetic, you get 1 and 234 out of 999, or when you reduce the fraction, you get 1 and 26 111ths, or if you prefer a mixed number, 137 out of 111. That's the rational number, or the fraction, that creates the repeating decimal 1.234234. In this example, we're asked to determine the common ratio of a geometric series with a given first term and infinite sum. The fact that the infinite sums are given tells us that these series do indeed converge. Pause the video and see if you can figure out what the common ratio would be for example A and for example B. Solving these problems is simply a matter of applying the formula. The infinite sum should be equal to the first term, which we're calling T1 in this example, over 1 minus r. So if my infinite sum is 12 and my first term is 3, I simply solve this equation for r. I find that 12 minus 12r is equal to 3, which then of course implies that negative 12r is equal to negative 9, and therefore the common ratio, r, would be equal to negative 9 divided by negative 12, or 3/4. And what that tells me is if I start with 3 and keep multiplying by 3/4 and adding all the terms together, I'll never surpass 12, but I'll get as close as I could possibly want. In letter B, we aren't so lucky. When we set up the formula this time, we find that 1 equals 4 over 1 minus r, which means that 1 minus 4 should be equal to r. And that, of course, means that r should be equal to negative 3 in order to start with a 4, add terms according to some geometric progression, and end up with an infinite sum of 1. Well, that is not possible because in order to do so, I'd need my common ratio to be a negative 3, but negative 3 does not fall within the requested interval for convergence, and thus letter B was a trick question. It can't happen. This example shows us a different way to think about these questions. We're asked to consider the infinite series that is described using a function of x. The function is 1 minus 2x plus 4x squared minus 8x cubed, and so on and so forth. And we're asked, will this function converge when x equals 1/2? Well, in order to determine that, let's plug in a half. When you plug in a half, you get a familiar series, 1 minus 1 plus 1 minus 1, and so on. Like the other alternating series, this one does not converge. And that's because after an even number of additions, we get 0, and after an odd number of additions, we get positive 1. It does not settle on a certain number. What about when x equals 1/4? What happens then? Well, this time you get 1 minus 1/2 plus 1/4 minus 1/8, and so on. And while the terms are alternating, I do see that the common ratio is clearly less than 1 and greater than -1. The first term is 1, and the common ratio is -1/2. And thus, it does indeed converge when x is equal to 1/4, and I can say that it will converge to 1 divided by 3/2, also known as 2/3. What about more generally? Find the interval of convergence. What values of x will lead to convergence? Which ones won't? I can see that x equals 1/2 is no good. Meanwhile, x equals 1/4 converges just fine. What are the bounds on x? Pause the video and see if you can come up with an answer. Solving this problem might seem difficult, but really it just goes back to looking at the function f of x and seeing what's happening between the terms. To get from 1 to -2x, I must multiply by -2x. And that same ratio is true all the way through the function. And thus, -2x is my common ratio. Now, normally, we need our common ratio to be between -1 and 1 in order for our series to converge. Well, if r is equal to -2x, then all I need to do is solve this inequality in order to figure out the interval in terms of x in which the series converges. Now be careful in solving this inequality because I have a minus sign in front of the x. And when I divide by a negative, of course, I need to spin the signs on the inequality, which leaves me with the statement 1/2 is greater than x, which is greater than -1/2. And it's more proper to write that inequality this way with the signs facing to the left. And so what we found is that any x in between -1/2 and +1/2, not including the endpoints, will converge when plugged in to this particular function here. I'll wrap this video up with a bit of a challenge. In this example, we're asked to solve for x. The equation, though, when we look at it, seems impossible to solve. On the left-hand side, we have a -1. On the right-hand side, we have an infinite number of polynomials added together. X to the first plus x to the third plus x to the fifth. The exponents keep growing higher and higher, and you keep adding more and more of them. And yet, when they're all added together, somehow, you just get -1. See if you can find a value of x in which this is true. We'll start off next class with sharing the answer. And thanks for watching.